All right, once again, back with another video here to go over major concept. Again, I strongly encourage you to, make use of the pause and buttons as well as the scroll in order to, have a situation where, if you're behind on something here and, you just need to hear it again. Oops, what did I do there? I want to open that back up. Um, close that browser there. Okay. Um, so, again, use those buttons, to navigate this video here, because you might need to see something again, and you also might need to fast forward through something. Okay, so rates of change. Another major concept we're going to talk about. Ultimately, we're going to find a derivative, which is an instantaneous rate of change for a function. And so to develop that idea, what we're going to first talk about is average rate of change. And essentially, if you're looking at this formula here, this is nothing but the slope formula, given 2 points. A, f of A, and B, f of B, all you're doing is taking the difference of the y coordinates divided by the difference of the x coordinates. And this diagram here and slope, this should all seem familiar to you. We do have a context here where we're talking about the change in the distance divided by the change of the time, and therefore we have an average speed. That's what the slope would indicate here. Okay, so, we're talking about miles on this axis and hours over here. And we take an interval of time, let's just say for t equal 0.5. So, 30 seconds or 30 minutes after after you leave somewhere, between 30 minutes and an hour, how far did you travel? Well, 25 miles. So we just take 25 divided by that 1/2 and we get 50 miles an hour. Now we know, if we were in a situation where the car were traveling consistently or stopping and going or whatever, the bottom line is that's the average, regardless whether you were going the same speed the whole time or stopping and starting and, going faster than 50 miles an hour and stopping at a stoplight, that sort of thing. Okay, so there we have it here. All this is just the slope of a line. Now, what we're going to do is kind of go on here and note that a lot of times we're going to have functions. If you look at all this, we just have some data points here and then straight lines connecting these. All right. But we're going to find out that these displacement functions or position functions or where something is on a graph, a lot of times is modeled by something that's curved. And so what we're eventually going to get to is cutting down this interval of time to being very close to zero, approaching zero. So you should, again, anticipate this idea of a limit. And we want to know how fast we're going at that particular instant in time. And so um, before we do that, here's just a kind of my math lab problem that you're going to have to do. You want to find the average rate of a function. All you're going to do is just calculate the y values by taking f of that function. And, so I just take f of 3 minus f of -1 and subtract 3 minus -1, which, again, 3 minus -1 is just has a difference of 4 there. And then you can go ahead and simplify this. So that's just a straightforward problem there. Now, what we want to get to here is this idea of taking and saying, all right, well, what about if we would go to, say, the difference of a function here that has 3x squared. Okay, so probably should have put that in here. Let me see. Let's do this. We're going to call this a function. I hate to do this while I'm doing this because it just makes these videos longer, but CS of t is equal to 3 t squared. Okay, so let's just go ahead and do that. Okay, so that's our function here. And what we're going to do here now is take a look and say, well, this gives us a position, and so t is time, S of t is a position. So in other words, at 2 seconds, I just take S of 2, put that in there. I take 3 times 2 squared at 12. We're going to say that their position is 12 units from wherever it is that we started. So if we call 0 the origin or where we start, then we're 12 units to the right of it. Negative values would mean we go to the left and so forth. All right. So now what I want to do is take the average. We're going to take the rate of speed here, how fast we're moving. We take the position here of, let's say, if h were 7. Okay, so if h were 7, I would take 10 plus 7. That would be where the function or that object is. It's 17 seconds minus where it is at 10 seconds, and then take the difference of time here, 17 minus 10. Now notice I have an h in here because I'm going to consider smaller and smaller differences of time between 10 seconds. So, between 12 and 10 seconds, what would be my average rate of speed here? Okay. Well, again, I'm just going to take S of 12 minus S of 10 over 12 minus 10. What about 11 to 10 seconds? What was the average speed at 11 seconds? Between 11 and 10 seconds. Well, again, H would be 1 and so forth. And you get that idea. So what I'm going to do is I'm going to develop a function here, okay, just to kind of speed that up and say, all right, well, let's go ahead and put in here 10 plus h. And if I take f of 10 plus h, all I'm going to do is replace the t with 10 plus h. I keep saying f, it's s. S of 10 plus h, I'm just going to go ahead and put in 10 plus h here. I'm going to subtract s of 10. So I put in a 10 for over here for the t squared and then divide by h. And then I'm going to kind of perform some algebra here. Here I use the distributive property or FOIL. So I'm going to take 10 times 10 and get 100, and 10 times h, get 10h, and then the inside would be 10 times h. I don't have this written out as two factors of 10 plus h. Not going to spend time with the algebra part of it, but that should be reviewed to you. And then finally, the last term is h squared. And so when I simplify all this stuff, distribute the 3 through, I basically get this in my numerator, okay, because the 300s cancel out. I factor out an h, cancel those out. I'm left with 60 plus 3h, okay? Now you notice I have over here pretty much that same deal here. I called this f, or I could call it h. It doesn't really matter what I use for the function value. But if I want to know at 10 seconds where this is, right, I just put a 10 in here, I square it, I get 100 times 3, I get 300. Well, I'm just doing that over here if I let this be my function 3x squared. Okay, so I'm using x's just because I'm in Desmos here. But over here, I'm using t and s over here, where over here I'm using x and f. Okay. Again, not to try to confuse you, but I just want to be consistent here with what Desmos can do. All right. So if you come down here, you look and see I have the same expression right here as what I have, because if I take 10 plus h minus 10, these are just going to cancel out and just leave h here. So I'm just going to express that as this right here. So if I want to know at, let's say when h is 7, I would have 17 here, right? So this will be f of 17 minus f of 10, and then 17 minus 10 would just give me h, right? 17 minus 10 is 7, so 7 would be here. And if I plug in, I get 81 here. Well, notice if I just plug into this expression over here, if I put a 7 in, right, for h, I'm going to get 60 plus 3 times 7, which would be 21, 60 plus 21, and get 81. So you can see that this expression right here, all I'm doing is just simplifying here, and I get this algebraic expression of 60 plus 3h. So if I want to know when h is, slide this down to 5, right? Okay, I just get 75 here in that expression. And I could use this one over here too, because now h is 5, right? If I just put a 5 in here for h, I get 60 plus 3 times 5, which is 15, and I get 75, okay? So you can see that this expression is equivalent to this ratio here, okay, which is really the same thing as what I have over here, all right? Now, what you're going to see is that as I go down as h gets to be, shorter and shorter amount of time here, we'll get into what the graph's doing over here. Okay. Notice I'm getting different values here, but this expression always matches up, right? The 4 in here is going to give me 60 plus 3 times 4. And so what I look at this is really, if I come back to this graph here, when I got a difference here now of whether it's 4 or 7 or 5, let's just deal with 5. Notice I go from 10 to 15, I get that little triangle or that slope. Well, if I connect those two dots, that's really looked at as a secant line, right? If you remember, from geometry, you have a circle, and if a line cuts it twice, we call that the secant. That's basically what we're calling this on the graph in calculus here, is that we're hitting that line in 2 points, and we're taking the average rate of change between those 2 points. But the function model is really a parabola or a curved line, okay? So what we're doing is we're taking the average rate of change of that function, which would represent the speed in this instance here. And the idea of what we want to do with calculus here is actually take that and by the way, this blue graph here, all this is just, see how this is the slope of that line, right? We're saying that's the slope. This is just point slope form. Y minus the y coordinate equals the slope times x minus the x coordinate, which is 10. And I just have those coordinates right here, and they're labeled right here. So f of 10 is 300, and that's where I am. So all this is the equation of the line. But what's nice about this is there's this dynamic. You can see it now, that point sliding around as h changes, as h goes from 8 down to, let's say, 5 or 6 here. You stop at 6. You can see it's over here at 6. And I could keep going. But what's happening here now is this idea, as that interval gets smaller and smaller and smaller, look what the line's doing. It's actually looks like or appears like it's getting close to just touching it at one point. Now it's not here. Okay, it's not touching at one point. We still got this little, if I zoomed in here, we'll be able to see this, that it's hitting in 2 points here. And so it's still a secant line. But what we're getting at here is that eventually there's going to be a limit of that. And what I want to do is, if I talk about the instant, the rate of change at the instant of 10 seconds, just at 10 seconds, notice if I got to h being 0 using that formula, my slope is undefined, right? Because I can't divide by 0. And notice the line actually disappears. It's not there anymore, all right? But it is pretty close to touching at one point, which we would consider to be a tangent function, okay? And it seems like that slope, right, of that line, yeah, it's 80 here, it's going down as I get closer and closer and closer. But as I get to that instant there, right where it's almost touching, I'm getting pretty close to the number 60. So if I go back to my algebraic expression over here, and I take that limit of this expression right here, this is just simplified. Remember, 10 minus 10 gives me just h. So if I take that secant line and take the limit as h approaches 0, and this expression just simplifies to 60 plus 3h. Now I evaluate that limit as h approaches 0. I use substitution. I get that limit is 60. Okay? And what that means is that therefore, if I consider the limit of that function, that secant line, as h approaches 0, that is going to give me this tangent line. Okay, so if I go ahead and turn this on, this is this red line. That's when the slope is 60. Notice now, I'll turn off this one. That red line is just hitting this. I'm going to turn this one off also. Okay. That red line is just hitting in that one point here, and that is a tangent line, and the slope of that line is 60. So what that means is that the average rate of change of that function, which would again designate speed, is going to be 60 miles per hour, 60 feet per second, whatever those units we're using here for the displacement and the time. Again, if it was miles per hour, then we would have 60 miles per hour is our instantaneous rate of change. And notice I have this little apostrophe here, f, we call that f prime of 10, and we're going to define the derivative, which is just essentially going to be a function here in a second that's going to give us that instantaneous rate of change. We're just at the beginning part of working with that here. I go ahead and turn this back on, turn that back on, okay, and take now this h and start dragging this around, okay. You can see that the bottom line is this: as h approaches 0, that secant line is approaching the tangent line, okay. You can see that that blue line starts to match up with the red line, okay. And that's what we're getting at. And notice, as h approaches it from either side, right? Because, when we get back to this, right, this is an undirected limit, right? So h is approaching 0 from both the left and the right, okay? And you can see that, that again is happening. If I get to the left, like negative values here and approach it, notice that's still happening, that the slope of that line is approaching the slope of the tangent line, okay? So it's pretty neat, dynamic, uh, visualization of what's going on here as that limit is, gets evaluated as h is approaching 0. All right. So to finish this up now, we get the idea of a secant line approaching the tangent line, and the secant line is the average rate of change, and the tangent line is the instantaneous rate of change. And so, when I talked about it back here, the average rate of change, okay, and then now when I move ahead here, I just did the Desmos, this is just some still stuff here. With this, we're going to talk about the slope of the tangent line being the instantaneous rate of change, okay? So if you look at this formula right here, all I did was my point A was 10, f of 10. That was for this specific scenario over here with this specific function, f of x equals 3x squared. So this is the general formula for the slope of a tangent line at a given point, okay? So this is only going to apply given a particular point, all right? And what we do with that then is say, well, let's just have a general function and not have a particular point A, but let's let x be a variable. And so now we're going to call that a derivative, f prime of x, okay? So where this is coming from, again, is the slope of a secant. We take the limit as h approaches 0 and say that's the instantaneous rate of the function at a given point A. But if we just want to have it apply for any point we want A, we'll just let that x be the independent variable and replace the A in that formula back here with an x. And now we actually have a function that is going to give us the slope of the tangent point at any x we desire. All right. So once we have that function, then we can go back and find f of a. Now I'll get into this here in a second, but there's a lot of stuff here, like I said, that's condensed, and this is why I want you using, you may have to stop the video there to think about that and read this stuff over and, scroll and replay it again. But if I get back to my example here, okay, and I want S of 10, what I did is I just go ahead and use my formula S of A plus H minus S of A, which is 10 over H. And I go ahead and go through this stuff here. I go through the algebra and I simplify here. Okay, all those values. 300s cancel out. I factor out the H, it cancels out. I get the limit as H approaches 0, 60 plus 3H, which we already talked about. And 60 plus 3 times 0, when I evaluate the limit, gives me 60. Okay, here's the derivative. Okay, so I'm just using t here, okay, instead of x, because t is my independent variable. But notice what I do here. I'm going to take s of t plus h. So I'm going to, again, use FOIL here. I get t squared, multiply the outside terms. I know I don't have it written out. It would be t plus h. The inside terms will be t plus h. So I have two of those, and then the last terms will be h squared minus s of t, which is just 3t squared, distribute by 3. And notice what's happening here. The 3t squareds cancel out. I'm left factor out a 3h. What happens here is that the h's cancel out. I'll distribute back through this 3, or I don't need to. In this case, I can just evaluate the limit. I could get the 6t plus 3h here, or just substitute the 0 in. Either way, I'm going to get 6t when I evaluate the limit. Okay. But here's the interesting part. Okay. Now, if I want s prime of 10, like I did up here, instead of going through all this for each individual instant, I can just plug into this formula. So s prime of 10 is going to give me 60. Okay, because why? 6 times, I get s prime of t is equal to 6 times t. So if I want the instantaneous rate at 10 seconds, I'm just going to go ahead and plug in the 10. I get 6 times 10, or 60, which is the same thing as we got up here. So now I have a function, if I wanted to, do this for, let's say, 8, the instantaneous rate of change at 8, okay, or 8 seconds, whatever t represents, then I wouldn't want to go through this and just have an 8 here, because I'm really going to end up with the similar pattern that goes over here. And essentially what I'll end up with is, if I want 8, I'm just going to take 6 times 8 and get 48. Okay, trust me, if I go through all this, I'm going to get 48. Well, it's a whole heck of a lot easier to just get this. And now if I want to know the change, instantaneous rate of change at 8 seconds, I just put in an 8. If I want to know at 7, I put in 7. I get 6 times 7, 42. How about 5? Well, I'm going to go ahead and take s prime of 5, and I'm going to get 6 times 5, and I get 30, and so on. All right. So that is the development of going from the secant to the tangent line with this limit. Okay. Ultimately, we're going to get a function now that again gives us that instantaneous rate of change. Now, in physics, what we call this is the displacement function. This gives the position of the object, and this gives the speed at any one given instant, which we'll refer to as velocity. Okay. And there'll be some position functions. This one doesn't happen to be moving in, it's never going to move in the negative direction. Usually we talk about particles moving on a straight line, and you'll get some problems like this. But because this function is always going to be positive, it's always going to be moving to the right, okay, and be a positive distance from the origin. Okay, so there we go here. Now, this is just kind of a preview. There's going to be easier ways to actually finding the derivative, okay? Just understand this, is that the derivative is if I start with a function that models some sort of phenomenon, this is just modeling a particle moving along a straight line, okay? So if we got a particle at 0 here at time 0, right? Put a 0 in here, 3 times 0, 0. At 1 second, it's just going to be 3 units to the right. At 2 seconds, it's going to be 12, right? Because I'm just going to put a 2 in here and I get 12. Well, the derivative is a function that gives me the instantaneous velocity at any given instant here. So at 0 seconds, the object's at rest. 6 times 0. 1 second, it's moving at 6 units per second. Okay? If t represented the time in seconds. But what I'm getting at here is, instead of getting this 6t going through all this limit business, we're going to find easier ways of evaluating limits using derivatives, and I'll do that next video. This is just kind of a sneak peek here. This is just a power function, and what the rule is we just take the exponent, multiply that times the base, so 3 times t squared, except I'm going to subtract 1 from my exponent. So I take the 2 down in front, multiply, subtract 1 here, and I take 2 times 3, and I get 6, and 2 minus 1 is 1, or t to the first power. So you would have to admit, going from here to here is a lot easier using that technique as opposed to going through all this to get my 6t. Okay, so this is a quick way of doing all this stuff right here, which is the derivative, evaluating derivative by the definition. We can also have theorems later on, or we will have theorems later on, which we're going to rely on. I'd hate you to do too many of these things, because you got a lot of derivatives to calculate in this assignment. And I'm just trying to, show you the development of why we go through all this, so you can understand that this is an instantaneous rate of change. But there's easier ways of getting that function later on in terms of how to calculate them, okay? And the ultimate here is there should be a prime here. That should be S prime of 10 is equal to 60, okay? Which is the same thing as what I got over here. All right, so that is that. What we're going to eventually do is do problems like this where we're going to find, equations for secant lines and then tangent lines. I'll do this next video. I probably should have just took this off of here and not had this, but I kind of had here, well, therefore we can find this in two separate ways. One is we can, if we want to find f prime of a, we can find f prime of x first and then substitute x equal a, or we can find, f prime of a by using this instantaneous rate of change method below. It's going to be a whole lot easier finding this because, like I said, we can use formulas or theorems like this later on, okay? Just some notational things to keep in mind up here. There are different ways of expressing the derivative, just like we, have functions. We can have a function y equals an expression x or f of x. So when we have f of x, we'll use f prime of x. When we have y equals, let's say y equals x squared, we express the derivative as dy dx or y prime, either way. Okay, so these are just three different ways notationally of expressing a derivative. Okay. And all this box over here gets into is just generalizing or summarizing that, again, this represents the secant. As soon as I take the limit, that is the tangent. And the tangent, again, has a special name, which we call the derivative, right? So that's that. Tried to keep that short as I could. Like I said, hopefully you use the scroll. You got to the end, you used the scroll and pause buttons to get through all the information that you needed to be emphasized here in this video. So we'll see you next one.